Hello, good afternoon, all. My name is Ravi Jaiswal, MTech 5th sem student, and today we will discuss about the data science end semester examination paper with solutions. So, there are 9 questions. So, the first question is distinguish between hypothesis driven and data driven programs. So, we will divide this question into three columns. First one is aspect, second is hypothesis driven, third one is data driven. So, the first is definition. Hypothesis driven start with a specific hypothesis, design data collection, experiment to test it, and data driven start with a data. So in this data, we have to explore patterns, formulate hypotheses, and from observations. The next point is approach. Hypothesis driven uses deductive approach. It will confirm and refute a stated claim. Data driven uses inductive approach, discover patterns, then generalize. Third one is workflow. Hypothesis driven has a workflow of hypothesis first, second one is experiment, then collect, then statistical test. Data driven has ingest data, and then EDA features extraction, modeling, hypothesis generation, validation. Next one is data needs. Hypothesis driven program needed smaller controlled experimental data sets, and data driven often needed large varied data sets, example logs, sensors, transactions. Hypothesis driven needed models like classical statistical tests, simple parametric models, and data driven needed exploratory statistics, machine learning models like clustering, ensembles, deep learning. Next one is strength. Hypothesis driven has a strength of clear causal testing with well designed experiments. Data driven has a state of good at uncovering unexpected patterns, flexible and data centric, and they have weaknesses also. Hypothesis driven has may miss unknown patterns, biased by initial hypothesis. Data driven has a risk of spurious correlations, require careful validation and holdout testing. The last one is examples. Hypothesis driven has a A/B test to see if new UI increases conversion rate. Data driven example is cluster using user behavior logs to discover high value user segment. Second question is differentiate between structured, unstructured, qualitative and categorical data. So we have divided into 5 sections. First one, we will talk about definition. So structured data is organized with fixed schema, means in rows and columns. Unstructured data has no fixed schema. It can be a text, images, video, and quantitative data is a numerical measurement. It can be continuous or discrete. Numerical means 1 2 3. Categorical data is discrete levels or categories, for example sex, race, hair, all these categories. Next one is storage. So structured data is stored in relational tables, CSV, SQL databases. Unstructured data is stored in text files, document stores, audio, image files, JSON blobs. Quantitative data is stored in numerical columns, in tables, in arrays, in time series, and categorical data is in the form of strings, coded integers in tables. Examples include of structured data like customer table. We have a column name, ID, name, age. So this is a table with structured format. And unstructured example is customer emails, product reviews, photos, call recording. These are also column names, but these are not in a particular table, means these are all unstructured. Quantitative has an example of age, salary, temperature, number of clicks. All are these are numerical data. Categorical has an example of country, product category, customer segment. Analysis techniques. Structured data is analyzed using SQL queries, aggregation, joins, classical machine learning models. Unstructured data analyzed using natural language processing, computer vision, audio analysis, and feature extraction. Quantitative data is analyzed using regression, correlation, hypothesis testing, distance based methods. And categorical data is analyzed using chi-square tests, frequency tables, encoding, and classification. Pre-processing is needed in structured data like schema validation, type testing, missing value handling. In unstructured data, it needed tokenization, stop word removal, embeddings, image resizing and normalization. Quantitative data needed scaling, standardization, min max standardization, outlier detachment like IQR tests. Categorical data needed pre-processing of one hot encoding, target encoding, handling and rare categories. Now let's talk about the second question A part. Sorry, it will be third. So in this, we have to compute mean, mode, median, standard deviation for a given smaller data set. So we will take our data set 2 triple 4 double 5 7 9, and we will sort it in ascending order. So what is the mean? Mean is we know as the sum of the all the values of the data set divided by number of values in the data set. So we will, so number of values is 8 and sum is 40, so the result becomes 5. 40 divided by f. Median is if the data is even, median is n by 2 and n by 2 plus 1 divided by 2. This is the answer. And if data is odd, the median is the middle term. So here it is even, so we have to take the average of fifth and 5 values, so it becomes 4.5. Mode is the most frequent value occur in a data set. Here we can see that 4 is occurred 3 times, so it will become our mode. Now the next one is standard deviation. Standard deviation means deviation from mean. So we have already calculated the mean, which is 5. We have we have take a difference of all the values from the mean. So 2 minus 5 is minus 3, 4 minus 5 is minus 1, like that. And then we will do the squares of all this deviation from mean, and after that we will do sum of it. So the sum becomes 32, and we will divide it by number of values in data set, which is 8, and we will take the square root of it. So the square root of 4 is 2, so that our standard deviation will become 2. The next one is when each measure is appropriate. When we should take mean, median, we have to classify that. So we will take mean in case of symmetric distributions without heavy outliers. In case we have not heavy outliers, median we will take in case of skewed distribution when outliers are detected. Mode we can use in case of categorical data or multimodal distributions. And standard deviation we will will be useful in case of measure of spread. Use sample standard deviation when inferring from a sample. So the next question is the third question B part. Difference between error and artifacts in data cleaning. Explain the imputation techniques, data imputation techniques. So what is the definition of error? Errors are incorrect or corrupted values caused by measurement plans, manual data entry mistakes, or transmission errors. Example: negative age, impossible date. And artifacts are the are also errors, but that are recoverable. So artifacts are systematic distortions introduced by instruments, data collection process, or pre-processing pipelines. Example: batch effects in genomics, sensor drift, compression artifacts. Now, what are the effects of error and artifacts? Errors often cause random or occur at row level and can usually be detected through validation rules and range checks. But artifacts affect a group of records in a systematic way and can bias analysis if not corrected. So we will also discuss two imputation techniques in these questions. So the first is mean median imputation. So we have to, in this we have to identify missing values in our numerical column. Then we will compute the mean or median in case if the data is skewed for all the non-missing values, and replace each entry with this mean or median. So and the next imputation technique is k nearest neighbors, KNN imputation technique. In this, we will select a distance metric and normalize features used for similarity. For a row with missing values, find k nearest columns with that feature. Impute numeric values by the average of neighbors for class. Categorically impute by majority categories. So now that's the all for this question. Let's do next one. So the next one is explain any four common feature engineering techniques for continuous or categorical data. So the first one is scaling, which is also known as standardization. In this, we will compute mean and standard deviation for numerical feature. transform each value of x to x modulus numerical sigma or scale it between 0 to 1 included with min max. Helps algorithms that are sensitive to feature selection, KNN, SVM, and gradient descent. Second one is one hot encoding. It is used for categorical variables in which for a feature with k categories, create k or k minus 1 binary columns. For column is each column is 1 if the record belongs to that category, otherwise it will be 0. Required by many machine learning algorithms that expect numeric inputs. Third one is polynomial or interaction features in which we will create new features in the form of polynomials like x square, x cube, x to the power 2 times for selected variables. Capture non-linear relationships while still using linear model. Should be combined with regularization to avoid overfitting. And the fourth one is binning, which is also known as discretization, divides the continuous features into intervals, bins of using equal width or quantile cuts. Replace actual values with bin levels, example low, median, high. Used to reduce noise, handle non-linear effects, or build interpretable rules. So this is all. Now let's see fourth B part. What is sampling? From a distribution, describe inverse transform sampling or Monte Carlo sampling with examples. So what is sampling? The process of generating random observations whose probability distribution matches a specified target distribution. Example normal, exponential. It is fundamental to simulation and Monte Carlo methods. What is inverse transform sampling? Let fx be the cumulative distribution function of the target distribution. Generate from uniform, which is from between 0 to 1. Set x equals to f under root of fu, the inverse quantile evaluated at u. The random variable x follows the target distribution. Now let's see their examples, which is CDF. CDF means cumulative distribution function, which is equals to e to the power 1 minus e to the power lambda of x, and the inverse is f to the power u divided by lambda x. For lambda equals to 2 and u equals to zero point 0.3, x equals to minus 1 by 2 logarithm of 0.7. Now we will see brief Monte Carlo sampling, in which we draw many independent samples dots from a distribution and estimated, used to approximate integrals, risks, and probabilities that are hard to compute analytically. So this is all for this. Now let's see next question. Next question is also a difference between parametric and non-parametric models, supervised and non-supervised, unsupervised models. So the aspect is definition. Uh, Parametric assumes a specific functional form with a fixed finite set of parameters, and non-parametric assume fixed functional form completely can increase with data size. Examples of parametric include linear regression, logistic regression, Gaussian, naive Bayes. Examples of non-parametric include KNN, decision trees, kernel density estimation. And parametric form has less flexible, can be biased if the assumed form is wrong. Non-parametric is also is not it is more flexible, can approximate complex relationship. The data requirement in parametric performs well with relatively small data sets when assumptions hold, and in non-parametric it is generally needs more data to avoid overfitting. Interpretability, often highly interpretable coefficients have clear meaning. Non-parametric can be harder to interpret complex trees or decision-based models. Computation sometimes has closed form solution, usually cheaper to train. Non-parametric distance computations or many parameters can be computationally cost. Now let's see difference between supervised and unsupervised models. So first we'll see definition. In the supervised we will see supervised learning, and in unsupervised we will see unsupervised learning. Examples include classification, regression. Examples of unsupervised include clustering, which is k-means clustering, hierarchical clustering, and association rule mining. The goal of supervised learning is predict or estimate the target variable as accurately as possible. And goal of unsupervised learning is discover clusters, latent factors, or patterns within the data. The data requirement in supervised learning is in the form of x comma y, and in unsupervised learning requires only features x, no labels, but means there is no pairs. In evaluation in supervised learning, use metrics like accuracy, precision, recall, RMSE. Unsupervised learning uses metrics with like score, reconstruction error, domain judgment. Use cases of supervised learning: spam detection, price prediction, medical diagnosis. Unsupervised learning has a use case of customer generation, anomaly detection, and exploratory analysis. Now let's see fifth B part. What is the definition of accuracy, precision, recall, F1 score, and illustrated using the confusion matrix? So we will all know the confusion matrix. What is it? It will be, we can see here like actual positive and actual negatives, and we will predict it with the help of predicted positive and predicted negative. So first we will see the formulas of accuracy. Accuracy is to- TP means predicted positive and it is actual positive. TN means predicted negative and it is actual negative, divided by all the parameters. Precision is TP divided by TP plus FP. FP means predicted positive and it is actual negative, and FN means predicted negative and it is actually positive. So recall is TP divided by TP plus FN, and F1 score is the harmonic mean of recall and precision. So let's see the calculations using this confusion matrix. So we will calculate we will have a total of 100, so the accuracy becomes 0.85, the precision becomes TP, which is equals to 50 divided by TP plus FP, which is equals to 60, which becomes 0.83. Recall becomes 50 divided by 55 because which is equal to 0.90, and F1 is the harmonic mean of recall and precision, which is approximately equals to 0.8696. So what is the interpretation we can get from these calculations? So first we will see precision. Precision is of all predicted positives, how many are truly positive, and recall is of all actual positives. We will notice here this is predicted positive precision and recall is actual positives. How many are correctly identified? And F1 is the harmonic means that I will discuss. So now let's see the next question, which is eighth. So in this we have to compare decision, random, forests, and boosting. So we will divide it into columns. So first aspect is core idea. Decision tree is a single tree that recursively partitions feature space using split. Random forest ensemble of many trees built on bootstrapped samples with features subsampling. Boosting is gradient boosting, sequential ensemble where each new tree is trained to correct errors of previous trees. And second aspect is bias. We can also say variance. Decision tree have a low bias and high variance, so it will become a prone of overfitting. Random forest is reduced variance relative to a single tree, similar or slightly lower bias. Boosting is typically low bias, variance controlled by regularization and learning rate. Training. The next aspect is training. Descent tree is fast to train simple hyperparameters depth mean sample. Random forest are parallel training our trees more computationally intensive. Boosting is sequential training, often slower but very accurate. Interpretability, highly interpretable, easy to visualize. Less interpretable, rely on feature importance measures. Low interpretable, boosting is needs tools as SHAP for explanations. Now next aspect is when to use. Decision tree we will use when we need transparent rule based model. Random forest use when we will need general purpose baseline for tabular data, robust out of the box. Boosting we will use when we need top predictive performance is required and compute is available. Weaknesses is unstable to small changes, overfits without pruning. Random forest is more memory and compute, and boosting requires sensitive to hyperparameters, risk of overfitting, and larger training time. So these are all the weaknesses. Now let's see the next question, in which we have to explain the architecture and components of Spark. This also we describe the advantages and disadvantages of our map reduce function. So in this we will first see Spark structure. Uh, The first one is driver program runs the main application and creates the Spark session, Spark context. Cluster manager allocates resources across the cluster. Executors work pressures on cluster nodes that run tasks and cache data in memory. Program abstraction, RDD, data frames, data set for expressing transformations and actions. Scheduler build, RDAG, direct acyclic graph for stages and tasks and schedules them. And executor. Now we will see the difference between Hadoop MapReduce and Apache Spark. So the first aspect is processing model. Batch processing with map and reduce stage. Each stage writes intermediate results to HDFS. If Apache Spark in uses in memory direct cyclic graph execution with lazy transformation and actions support batch streaming interactive workloads. Second aspect is performance, disk, high disk and network IO, slow for iterative or interactive algorithms. Apache Spark keeps data in memory where possible, much faster for iterative machine learning and interactive analytics. API ease of use, low level API reduce functions, more boilerplate code. In Apache, we will use high level APIs like data frame, data set, SQL, my library allows concise expressions. And then last aspect is machine learning and streaming. So the Hadoop MapReduce uses needs external tools. MapReduce not alone ideal for interactive ML and streaming, but in Apache Spark it includes Matplotlib library for scalable machine learning and unstructured streaming for real-time processing. So, friends, this is all for this and some papers. And I hope you all understand all the concepts related to the questions. So, let's meet in some other video. Till then, take care.